HS 4.1, Jaundice. If you recall back to the previous HS 3.1 on the liver and the biliary system, you'll remember some of the functions of the liver, such as detoxification, process and storage of amino acids, lipids, etc., the immune function, and biotransformation, getting rid of ammonia, for example, and also synthesis of bile acids from cholesterol. Now, this bile that is excreted from the liver into the hepatic ducts and common hepatic duct and then common bile duct, this also contains something called bilirubin, and that essentially is what causes jaundice. Bilirubin. Jaundice is, as you probably know, it's yellowing of the skin and sclera of the eyes, and it's a result of bilirubin buildup in the blood, so it's called hyperbilirubinemia, too much bilirubin in the blood. I'm going to talk about the sort of the life cycle of the red blood cell in a minute, talk about how you get to bilirubin eventually, but first I'm going to introduce some of the liver tests that you can do, some of the chemicals involved and enzymes involved in the liver. So first of all, you've got bilirubin, that's one of them. There's hepatocellular enzymes, which are to do with the liver cells themselves, such as AST and ALT. These indicate sort of how well the liver cells are functioning. Hepatobiliary enzymes, these are involved in the processing of bile and bilirubin, such as alkaline phosphatase, ALP, and glutamyl transferases. And finally, protein synthesis, because protein synthesis is one of the functions of the liver, so albumin and clotting factors. And if you do blood tests and you find that someone's got a lot of hepatocellular enzymes, so AST and ALT, raised levels of AST and ALT, it indicates damage to hepatocytes, and for whatever reason, that could be hepatitis, for example. Raised levels of hepatobiliary enzymes, ALP and glutamyl transferase, indicate biliary obstruction and cholestasis, which means blockage of the bile duct. And protein synthesis, albumin and clotting factors, raised albumin, raised clotting factors, indicates damage to liver functions, which is the most important. Bilirubin is a product of heme catabolism, so let's have a look at how that happens. Well, let's start in the bone marrow. So in bone marrow, erythropoiesis happens, which is the production of red blood cells. Bone marrow makes reticulocytes, which are red blood cell precursors, which then become erythrocytes, which are red blood cells, move in the blood, carrying oxygen for 120 days. Then what happens is, after their time is up, they are then taken up by macrophages. Macrophages break down the hemoglobin into its constituents, heme and globin, as shown here. The globin goes back to the bone marrow for erythropoiesis, and the heme is broken down further to give iron and something else. So heme is broken down to biliverdin, which is green, and then bilirubin, which is orange. Now what's special about this bilirubin is that it's unconjugated, which means that it doesn't have a glucuronic acid. It's not bound to glucuronic acid. So this unconjugated bilirubin, it's insoluble in water, and so therefore it's carried in the blood by a protein called albumin, right, which binds to it. The albumin and unconjugated bilirubin travel to the liver, where it's actively transported across the liver membrane, and in the liver it's conjugated, as shown here, this conjugation step here, with glucuronic acid by an enzyme called UDP, glucuronal transferase. And this forms CB conjugated bilirubin, as you can see here, the glucuronic acid conjugated on it. Now what's different about the conjugated bilirubin compared to the unconjugated bilirubin here is that it's water soluble, so it doesn't need to be bound to albumin. So then what happens is this conjugated bilirubin, it is excreted into the bile duct, into the duodenum, shown here, through the small intestine into the large intestine, and in the large intestine it's metabolized in the intestinal tract by intestinal bacteria called beta-glucuronidase bacteria, which converts the conjugated bilirubin into urobilinogen. Well, it converts it to unconjugated bilirubin, so back into unconjugated bilirubin, and then urobilinogen, which is colourless. And what happens is that 10% of this urobilinogen is reabsorbed back into the portal vein to the liver. So that's the intestines, hepatic circulation back in like this. And 90% is converted to stercobilinogen, again by bacteria in the colon. Stercobilinogen, which gives feces its brown colour. So to summarise, the red blood cells are broken down to biliverdin and then bilirubin, which is unconjugated bilirubin. Unconjugated bilirubin becomes conjugated in the liver by adding glucuronic acid by UDP glucuronyl transferase enzyme, which then goes to the large intestine where it becomes urobilinogen and becomes stercobilinogen in the colon, which gives stool its brown colour. Now this urobilinogen, which is reabsorbed into the enterohepatic circulation, when it enters the liver, some of it goes to the kidneys where it's renally excreted, giving urine its colour, and some of it enters back into the bile duct. So that's the enterohepatic circulation going like this. So as I said, jaundice is raised serum bilirubin hyperbilirubinemia, which is seen around the eyes, so the sclera and the skin.